This video we're just going to discuss the heat box that we're going to use in the next few labs. So this is a picture of the box here, and if you look at the terminal block up here, we have it pre-wired to an internal circuit. So it has the pin values here. We have 24 volts for pin 1, then ground, then we have direct heat control, and then a MOSFET to control the heat, and a MOSFET to control the fan over here on the edge. And there's also 2 internal temperature sensors. So this is just a look at inside the box here. Down at the bottom is the whole setup here. So we have 2 power resistors here with a temperature sensor sitting here measuring the heat at the resistor, and then we have 2 power MOSFETs and a voltage regulator. The voltage regulator is really just in there to set the voltage properly for the internal temperature sensors. And so this is the wiring diagram. We have our power MOSFETs here, and we have a gate. The gate of the MOSFET is connected to an 8.2 kilo ohm resistor to ground to allow it to discharge when you shut it off. And then your input here, we need to put an input voltage of about 20 volts into the gate to turn on the MOSFET. So when you turn on this MOSFET, what that does is we're going to have 24 volts over here. That 24 volts will now come down through here and power these 225 ohm resistors, heating up the box. So this MOSFET will heat the box. And so again, we have the we're going to put 24 volts here. That's pin 1 is the 24 volts, and that's connected to the high side of the resistors. And we also have the red LED here, so it's a 24 volt LED. So when you activate this, or you put 24 volts here, but then you have to either turn on the MOSFET or use some external control through this. So we have 2 different ways to control it. We can control it externally through this pin, through an external MOSFET or BJT or relay or something that we want to control over here, or we can use the internal MOSFET to activate the heaters. Then over here on this side, well, right here in the middle is just the voltage regulator with some resistor here. Again, the purpose of the voltage regulator is just to power the temperature sensor. Now this is just showing 1 temperature sensor, but we actually have 2 of them placed inside the box, and so we have 2 connections for those. And then we have the MOSFET that activates the fan. Now we don't have an external control for the MOSFET. We just have the internal MOSFET, which will activate a 24 volt DC fan. And again, it's just got this 8.2 k ohm resistor here just to allow it when the gate goes low, we need to just make sure that there's a path to discharge that current or that charge at the gate of the MOSFET. So we have a 8.2 k ohm resistor. All right, now we're not going to use the internal temperature sensors. We might use one of them, but we also are going to use the RTD. So RTD is a resistive temperature device. We can use this to measure temperature. And so I talked earlier about that in the video here, but this is the wiring diagram. And what we're going to do is we're going to use our analog output to output 10 milliamps of current out of our PLC. And then we're going to drive that through the RTD. Now the RTD here, an RTD can handle 10 milliamps, but it'll get a lot of internal heating. So we don't want it to get too hot. But the reason we're using 10 milliamps is just that the higher currents, the analog card can maintain a constant current more accurately. So we want to maintain an accurate current over here. And then what we're going to do then is put in a shunt here to bypass some of that current. So we're going to end up with about 2.5 amps of current through the RTD circuit, and then we're going to measure the voltage across that to determine the temperature, and then we'll have to scale that temperature inside of our PLC program. So this table here just shows the layout of the RTD for the actual resistance of the RTD. So if you are at a 80 degrees Fahrenheit, then the actual resistance of the RTD should be about 110 ohms. And so if we're putting a current in it of about 2.48 milliamperes, then that should give us a voltage across it of about 254 millivolts. And so and there might be a little bit of self-heating due to the 2.5 milliamps. Usually we want to keep that current pretty small, but this self-heating would be much higher if we put all 10 milliamps right through the RTD. So because it's kind of exponential, so as you put more current, it's going to get even hotter because there's less chance for it to dissipate. So basically what that means is that for a 80 degree temperature, the RTD might actually be closer to about 80.25 due to that internal heating. So see, the internal heating isn't real significant at this point, and it's pretty consistent between about 80 and 120 degrees Fahrenheit, which is about where we're going to operate the system at. Alright, so if that's the case, then we're going to read the voltage in. So when we read the voltage in, we want to, we're going to use the integer value in here, and it's going to come in as a count based on the analog to digital conversion. So this is basically a binary conversion of the voltage. So we have a voltage that's, you know, over here 253 to about 258 millivolts. And so the voltage range about that is actually just going to be a count of about 27 degrees, or 27 counts, sorry. So we've got 40 degrees is about 27 counts, so that's about a count per degree, right? Just a little bit under a count per degree. So it's not real sensitive doing it this way, but it's sufficient for our purposes for the lab. Okay, so here is basically what we're looking at for our ladder logic program here. So we have this, our first rung, of course, is going to be our fill-in circuit. So we'll use the start and stop buttons pre-wired into the PLC, along with the red light inside the PLC. So what this is going to tell us here, the red light is going to be our fill-in bit, and the red light will come on when the system is on. Okay. So the next thing then we're going to have to do is scale the voltage, or scale the voltage reading from the temperature sensors. Now the ones shown here are for the internal temperature sensors, which are the TMP36, and so we're reading in the temperature voltage as a count. So this is a count, and then we're going to scale that using the standard scaling equation, y is equal to mx plus b. And so I have a tag called m temp 36 and b temp 36. Now these are real tags that I can use to calculate my scaling. So what we're going to do is we'll use an actual temperature gauge. I have a digital temperature gauge we'll stick in there, and we'll set the temperature. We'll find a low value and we'll find a high value, and we'll calculate the scaling. Now we're going to use the RTD, so the scaling values might be different or whatever for that, but basically the compute statement is identical. It's just a matter of what values do you use for your M and your B for your slope. So we'll have to measure that and calculate those values. And again, I was doing this for both temperature sensors. We're going to use an RTD for one, but you can actually also use one of the internal temperature sensors. We only have two of the voltage analog inputs wired up to the terminal block, so we can only have two temperatures coming in, so we can't use all three. Alright, so but then my control here, I have a less block, and I'm saying, okay, well, if the actual temperature after I scaled it, and I'm using the first one here, so if my actual temperature is less than 0 degrees, then I'm going to turn off my fan. And if it's too high, so in this case I had in here 115 degrees, so if the temperature is above 115 degrees, I'm going to turn the fan on. Alright, so notice these here are just virtual bits, fan on and fan off. And then what I'm going to do is I'm using a timer here to activate this. So I'm actually going to use a timer off, so when I enable this, it's going to turn on the timer, and when it shuts off, the timer is going to keep running for a little bit. And the reason for this is that when you're doing something, some kind of control like this, if I just had it, if I just had these booleans turn the fan on or off, I would only need the fan on, right? I wouldn't need the fan off. I'm not even quite sure why I put that in there, in here. But this, to turn the fan on, when this was on, okay, so if this goes on, the fan's going to turn on, but as soon as the temperature drops right below that value, the fan shuts off. And so the fan is going to be, especially with a little bit of noise in there, the fan would be on and off just very erratically, and it's just a lot of current starting and stopping on that inductance of that fan. It's not good for the circuit, it's not good for the MOSFET or whatever. So what we want to do is slow it down a little bit. So the idea is when I turn the fan on, I want it to run for at least 30 seconds or 10 seconds or whatever the case may be here. Okay, so I think this was actually a typo. I think this was supposed to turn the heater on, and so I said too cold, but I said the fan is off. Should just be heat on there most likely. But this, so what I'm doing here is I'm going to, if it's too cold, we're going to turn the heater on. Now here I'm just using a move block, and the whole purpose of the move block is to move in a preset for my timers into the timer preset. All right, so remember you have the preset for the timer here, but the problem is that if I just hard code it to 200, if I just hard coded that preset to 200, I would not be able to modify it on the fly or through an HMI or some sort of change. I would actually have to, go offline, turn this system offline, change it, and then download it again, which is kind of clumsy. So I don't want to do that. So that's what I'm moving this tag into place, and then this tag I can easily change that on the fly. So that's what I'm doing there. But yeah, too cold means we're going to turn the heater on. And again, we want to keep the heater on. Once we turn it on, just there might be some noise or something, so that maybe the temperature, or due to the noise, it looks like the temperature dropped down below or above for the high, too high one, and get like a false hit. So once it crosses that threshold, we're going to activate either the heater or the cooler. But then once it's done, maybe the temperature drops back into the good range, but we're going to keep that activated for a few more seconds. And again, that we can change this on the fly using this tag that we set. All right, so then on this rung here, what I did then was I actually created kind of like a bit of a sill in here to or an OR sort of block here, not a sill in, but an OR block here, so that I could force the fan on using the selector switch, or the automatic control could activate it. Okay, so here we're actually turning the fan on, so we're putting a high to the gate MOSFET for the fan. And so if the control says it was too hot, then it's going to turn the fan on here. But if I just want to turn the fan on myself, I can just flip the selector switch to position 3, and that'll just turn that fan on. So that's what we're doing there. And then I have sort of the same thing over here where I can just keep the heat on all the time. So if I put the selector switch in position 2, then I can turn the heater on and it will stay on all the time. And as long as I have it in position 2, or if not, if the temperature was to drop below the too cold value, then it'll turn on the heater. Okay, so that is the program there. I just have 8 rungs, and you could argue you could maybe make it a little bit shorter, but this I think's a pretty good program. I had it running, and it seemed to run very well.